So it'd be nice to develop an equation if we launch an object on flat ground to define how far that object's going to go. And we're going to do this with just variables so that we can use this then later on when we're given any set of numbers. So let's say an object is launched with a velocity of v0 at an angle theta. And it's going to hit the ground, again, on level ground, flat ground, some distance further down. We want to find out what delta x is. We'll call that the range. How far is this object going to go? Well, again, a kinematics problem. We have x and y, and we're going to find our initial velocity in the x as v cosine theta and initial velocity in the y as v sine theta. And we'll put those into the chart. We know the acceleration in the x is 0. Nothing's making this speed up or slow down in the forward or backward direction, but we do have gravity pulling it down. We call positive up, so in this case gravity will be negative g or minus g. So g will be the number and the minus sign is already put in there. It's going to go some distance delta x, and in the y direction the displacement's going to be 0 because it's going to land back where it is. So it may go up in the air, but it comes back down, and overall it lands at the same height where it started. Displacement in the y is 0. The times will be the same for each of these. As soon as it starts moving up, it starts moving forward, and then both watches would stop when it reaches the ground. So we look at the four variables we have, v0a, delta x, and t, and we see that that's our equation. Delta x equals v0t plus 1/2 at squared. Delta x will then become v cosine theta t because there is no acceleration. And delta y, which is 0, becomes v sine theta t minus 1/2 gt squared. Now we have two equations where we want to go through and solve. We have three unknowns though. We have time, velocity, and delta x. But we can get rid of these values and just set it up so that we have what we're looking for. So what we do is we take the y velocity or y equation and solve it for time. So we can factor out a t, and that means that t equals 0, or that whole v sine theta minus 1/2 gt is equal to 0. We factored out a t, so it's just gt, not gt squared. Then we can use that second term and solve for t. And we find that t is v sine theta over 1/2 g. And I don't like having that half in the denominator, so we can multiply numerator and denominator by 2 to get rid of that. So we have 2v sine theta over g. Remember, that's time, and we're going to substitute that into the x equation so that we'll bring that down here, and we get delta x equals v cosine theta t, but we use our new value for t. In this, we have 2 cosine theta sine theta. 2 sine theta cosine theta is a trig identity. If you remember way back to doing trig identities, or if you haven't done that yet, the idea is that there are relationships between these. And what we have is we have two values of theta, but we want to rewrite this as something with one theta. Kind of like if we're solving for x, we got to get x by itself or a single x. Looking at the geometry in triangles, 2 sine theta cosine theta will result into equaling sine 2 theta. See, and you never thought you'd use trig identities. So now what we're going to do is we're going to rewrite our delta x equation. We have a v times a v in the numerator. We write that as v squared. We take our 2 sine theta cosine theta and we write that as sine 2 theta all over g. And we call this the range equation. Remember, this is only good, it only works when delta y equals 0, because we put that 0 into our problem. So once we lock that number in, and remember that's the only number we used, everything else was variables, so we can use it for any situation in which the object lands back at the same height it was started. The other thing to remember that g is just 9.8. We said that the acceleration in the y is minus g, or the opposite of g. So 9.8 is g. If we put g as minus 9.8, we'd have a minus, and then that would become positive. So remember, g is just positive 9.8.